From a distance, the closest planet to the Sun looks like a standard crater-pocked rock, but structurally it behaves more like an incredibly dense iron cannonball. This cross-section compares Mercury to Earth. Mercury's iron-rich core takes up 57% of its total volume, while Earth's occupies 17%. Between the core and crust normally sits a rocky mantle. On Mercury, the vast majority of this expected layer is simply missing. A celestial body does not naturally accrete with these proportions. The object orbiting our Sun today is the surviving wreckage of a massive cosmic subtraction. Early in the solar system's history, a massive roaming planetesimal, roughly a sixth of Mercury's mass, collided directly into the young planet. The sheer kinetic force of the impact violently stripped away the original thick outer crust and mantle. That rock was scattered into deep space, leaving behind only the oversized, dense metallic core. This physical trauma crippled the planet. By tearing away its thick outer insulation, the collision left Mercury entirely exposed to the harshest environment in the inner solar system. Today, Mercury lacks a true atmosphere. Instead, it has an exosphere, an extremely thin, surface-bounded layer of trace gases, where atoms rarely even collide with one another before being continuously blown away by the solar wind. Because an exosphere is far too tenuous to trap heat, the planet's surface is left completely at the mercy of the surrounding thermodynamics. This data visualization charts the resulting chaos. On the day side, the surface cooks at 430 degrees Celsius. But step over the terminator line into the night side, and the temperature immediately drops to negative 180 degrees. The planet's slow 3-2 spin orbit resonance turns this into a grueling cycle. A single solar day lasts 176 Earth days, locking the surface into months of deep, freezing darkness, followed by months of relentless solar baking. Mercury is a thermodynamically broken world, entirely incapable of insulating itself from the nearby Sun. The trauma extends deep below the surface. After billions of years, that massive exposed iron core is steadily losing its remaining primordial heat to the vacuum of space. As the core cools, it solidifies, and as it solidifies, it physically shrinks. This process is called planetary contraction, and it reduces the overall diameter of the planet. Because the outer crust is already a cold, brittle solid, it cannot smoothly shrink to fit the receding core. Instead, the shrinking interior generates immense compressive stress on the shell above it. Under crushing pressure, the surface fractures. The crust snaps and thrusts over itself, forming steep, cliff-like ridges called Lobate Scarps, running for hundreds of miles. Mercury is actively crushing itself. As its internal heat engine fails, the planet is collapsing inward under its own weight. Skip ahead 7 to 8 billion years, and this slow decay finally hits a wall. Our Sun will eventually exhaust its supply of hydrogen fuel. When that happens, the fusion reactions holding it stable will collapse, pushing the star into its red giant phase. The dying star will swell. Its outer layers will expand violently outward, consuming the empty space of the inner solar system. The same star that has tormented the planet for billions of years will become its executioner. As the swelling solar atmosphere reaches Mercury, it will generate immense physical drag on the planet, causing its orbit to permanently decay. Mercury will cross the threshold first, becoming the first planet in our solar system to be entirely engulfed by the expanding Sun. Before the rock touches the star, ambient heat will liquefy the iron crust. Moments later, a wall of solar fire will vaporize the liquid remains. It is a world born in violence, existing in agony, and destined to end in fire.